How's it going, everyone? The subject of this video is the identity matrix and the matrix inverse. So this has to do with matrix multiplication. If you haven't covered that yet, if you haven't seen the video on that, you can check my earlier video on matrix multiplication. You'll have to know how to multiply matrices in order to understand this video here. So the identity matrix, okay, this is specifically for multiplying square matrices. The identity matrix is typically represented with the letter I, and it's a matrix such that if you multiply it by any matrix with the same dimensions as would be needed for this property here, you'll get the same matrix A that you started with. And the order doesn't matter. So if you do matrix A multiplied by the identity matrix, you will also get matrix A as a result. This is equivalent to multiplying a number by 1. As a result, you get the same number. So here we have I and A are both n by n matrices. Okay, so these are square matrices of the same dimension. And what the identity matrix looks like is it looks like this. So you have ones along the main diagonal and zeros everywhere else. Okay, so for example, if you have a 3 by 3 identity matrix, it would look like this. And if you have a 2 by 2 identity matrix, it would look like this. And as an example, let's say we have A equals 1, 2, negative 3, 4, and we calculate I times A. That's going to be right. So we're taking the dot product of these rows with these columns, and those will be the entries to the matrix that results. Okay, so first these two, 1 times 1 is 1, plus 0 times negative 3 is 0. Then these two, 1 times 2 is 2, plus 0 times 4 is 0. And then these two here, 0 times 1 is 0, 1 times negative 3 is negative 3. And then these two, 0 times 2 is 0, 1 times 4 is 4. And so, of course, we get matrix A as expected. That's how the identity matrix works. Now, many matrices have something called a matrix inverse. Okay, so if we let A be an n by n matrix, okay, then B is the inverse of A, written A with an exponent negative 1 there. Okay, if B multiplied by A equals the identity matrix, and A multiplied by B equals the identity matrix. In other words, if a matrix has an inverse, and not every matrix does, okay, but if a matrix has an inverse, then a matrix multiplied by its inverse is the identity matrix, and the other way around, the inverse multiplied by that matrix is also the identity matrix. And if B is the inverse of A, then A is the inverse of B. Okay, so the inverse of an inverse is the matrix itself. Okay, so two matrices are inverses of one another. Okay, that's what the matrix inverse is. Now, again, not every matrix has an inverse. If you have, for example, A equals 1, 2, 0, 0, well, there's nothing you can multiply this by. There's no matrix you can multiply this by to get the identity matrix. Okay, because these zeros here will ensure that you have zeros in the bottom row, which means you can't get that 1 there. Okay, so not every matrix has an inverse, but those that do, there's different ways to find them. Okay, so for example, let's let A equal 1, 2, 0, 1. Okay, and we want to find the inverse for this. Okay, so we want to find a matrix that if you multiply it by A, you're going to get the identity matrix. And there's different ways to do this. Okay, we could think, okay, let's say A inverse equals A, B, C, D, whatever that is. And then we can say, okay, A, B, C, D times 1, 2, 0, 1 equals 1, 0, 0, 1. Okay, and you can solve this as a system of equations, right? So you could say, okay, A times 1 plus 0 times B equals 1. Okay, that's that first dot product there, right? So this row dot product with this column should get us this value right here. And you could do that for the other combinations of rows and columns, right? So you could say that A times 2 plus B times 1 should get you 0, right? So that's the dot product of these gets you that 0 right there. You could say C times 1 plus D times 0 gets you 0. Okay, that's these two multiplying gets you that 0 there. And you could say C times 2 plus D times 1 gets you, okay, that's that right there, gets you 1. Okay, so you have a system of 4 equations and 4 unknowns, and you can solve it, right, as a system of linear equations. You could put it in matrix form. You can just solve it straightforward without putting it in matrix form, and you'll get your answer. All right. So there's those two ways to do it, right? There are other ways to do that as well. Okay, so if we were to solve it right here, okay, let's say in matrix form, right? So let's set up a matrix. Okay, so our first row is going to be A, right? First column A, B, C, D, and then we have our augmented matrix here. So we have 1A equals 1. Okay, so there's our solution. We already know A equals 1. Okay, we know that 2A plus 1B gives you 0. Okay, we know that 1C and 0D gives you 0. Okay, so that already tells us C equals 0. Okay, and we know that 2C plus 1D gets you 1. All right, so you could bring this to row echelon form, get your answers. You could take this information right here, right away, to get your answers, right? Because if A equals 1, right, then this equation here tells you, okay, so 2 times 1 plus B times 1 gets you 0. 2 plus B equals 0. B equals -2, right? And from this equation here, you have 2C plus D equals 1. You know that C equals 0, which tells you that D equals 1. Okay, and there's your identity matrix, right? A, B, C, D is equal to 1, -2, 0, and 1. Okay, and if that's your identity matrix, well, we can check, does it work, right? So that's your inverse matrix, right? So inverse of A multiplied by A, that's going to be 1, -2, 0, 1 times 1, 2, 0, 1 right? Let's see if that works out. So we'll be taking the dot product between these rows and these columns. All right, so let's take the first one there. 1 times 1 is 1, plus negative 2 times 0, that's 0. This one here, 1 times 2 is 2, plus negative 2 times 1, so 2 minus 2, because that'll be a negative 2. Then in the bottom here we have 0 times 1 plus 1 times 0 is 0, and 0 times 2 plus 1 times 1 is 1, right? And of course that does equal the identity matrix, so yes, we found the matrix inverse. Okay, now this is one way to find the answer, but here, okay, it was rather easy to do it because we're dealing with a matrix that has a 0 in it. We're only dealing with 2 dimensions. Okay, here's a more general way of finding the matrix inverse. Okay, so let's say, and we'll do 2 examples, two dimensions as an example. Okay, so let's say A equals A11, A12, A21, and A22. Okay, and A inverse, okay, we're going to call that B11, B12, B21, and B22. So A times A inverse, right, it should equal the identity matrix, right? So 1, 0, 0, 1. So if we put this in general form, right, and we'll take those associated dot products, okay, so these rows with these columns, okay, we get the following. Okay, so A11 times B11 plus A12 times B21, well, that should equal 1, right? Because that's this dot product here, which should give us that 1 right there. Okay. Now, A21 times B11 plus A21 times, A22 times B21, well, that should equal 0, right? Because that's this this dot product, and it should give us that 0 right there. Okay, so this is a system of equations which can be solved with an augmented 2x2 matrix, right? If we have one column representing B11 and the other column representing B21, right? We have A11, A12, A21, A22, and that's it, right? We can solve this augmented matrix, put it in row echelon form, we'll get what B11 should be equal to, right? And we'll get what B21 should be equal to, right? Because eventually we'll get 1, 1, 0, 0. If we do reduced row echelon form, we'll get B11 right here and B21 right here. Okay, once we reduce that, okay, because we're used to thinking of it as like this column being X and this column being Y, right? And we put it in reduced row echelon form and we get the value for X right here and the value for Y right here. Okay, so that's what we could do to get the first column of this matrix. Okay, what do we do to get the second column of that inverse matrix? Okay, well, it's actually going to look like this. A11, A12, A21, A22, augmented matrix with 0 and 1 instead of 1 and 0. Okay, where this is going to be B21 and this column represents B22, right? Because that's how your dot product will work out, right? You're going to have A11 times B12, A12 times B22, right? You'll add those, and then you'll have A21 times B12, right? And A22 times B22. So what you can actually do, you can do an augmented matrix with 2 columns after the vertical line. And you'll notice that's the identity matrix on the other side of this augmented matrix right here. And if you bring this to row echelon form, reduced row echelon form, which you'll notice is also the identity matrix, well then what you'll get here is B11, B12, B21, B22. Okay, now that may seem like a strong claim, so let me show you. All right, let's take that same matrix that we worked with before and bring this left side to reduced row echelon form. All we have to do here is actually row 1 minus 2 row 2. All right, so what we get okay, 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0. 1 minus 2 times 0 is 1. 0 minus 2 times 1 is negative 2. And there we have it. Okay, if this is A, this is the same A inverse we calculated a longer way before. Okay, and for 2 dimensions, simple matrix, it makes a little bit of a difference, but once you get into 3 dimensions, 4 dimensions, and so on, finding the inverse matrix in this way is much quicker. And another great application of the inverse matrix, if we have an equation like this, a matrix times a vector equals some other vector, okay, we can solve it using the inverse matrix. Okay, so let's say A is going to be what we're used to it being, right? And let's say B is equal to, let's say, 3 and 2. All right, so what exactly does this equation mean? Okay, so we have 1, 2, 0, 1 multiplied by x1, x2, and that equals 3 and 2. All right, so this matrix equation, okay, we're treating this vector as if it is a matrix with just 1 column and 2 rows. So we'll do this row and this row dot product with this column, and what we'll get is, so 1x1 plus 2x2, right, and 0x1 plus 1x2, right? That's our matrix with 1 column, which is also a vector, right? And that's equal to 3, 2. So we have x1 plus 2x2 equals 3, and x2 equals 2. So this is a system of linear equations, and of course you can solve it as an augmented matrix like this. Right? So a matrix equation like this, it's just a system of linear equations, right? It's what you've seen before if you've seen the previous material that we've covered here, right? So we could take this, bring it to reduced row echelon form and so on, right? Or we could do the following. Okay, so if ax equals b, right, we can multiply both sides by A inverse. And then we get the identity matrix on the left side equals A inverse times B. The identity matrix multiplied by any matrix, and we could think of this vector as a matrix, is itself, right? So what we get, x equals A inverse times B. All right, so there we go, we've solved it. So if we know what A inverse is and we know what B is, we can solve for x, right? We can just take that B, which is 3, 2, multiplied by A inverse, which we've already calculated, right? So 1, negative 2, 0, 1 times 3, 2, okay? So we get 3 plus negative 2 times 2 on the top, and we get 0 times 3, so 0 plus 2 times 1 at the bottom, and this gives us negative 1, 2. And that's our answer. That's what x1 and x2 are equal to. Okay, if we were to take this, right, bring it to reduced row echelon form, okay, row 1 minus 2 row 2, what does that give us? So 1 minus 2 times 0 is 1, 2 minus 2 times 1 is 0, 3 minus 2 times 2 is 3 minus 4, which is negative 1. So of course it gives us the same solution for x. And for 2 dimensions, for a simple matrix, it might not seem like it makes a difference, but for more dimensions, for more complicated matrices, this is often a simpler way of solving systems of linear equations and of solving these kinds of matrix equations. So, I hope you enjoyed that, and I'll see you next time.